So last time we take probabilistic roadmaps, okay, and basically the main objective of this probabilistic roadmap is to build a map, okay. So the robot is in some environment, and probably if you just use the grid, map, it will be very memory inefficient or memory very expensive. You need very large memory, okay. So instead we do the probabilistic roadmap. We just generate random nodes and we try to connect them in a graph. Then later this will be your map. Later when you have a start and a goal, you just deploy these nodes, try to connect them to the closest node in that graph, and try to use, for example, a star or whatever to connect the start and the goal. Okay. Now, some other times you already also have big environment, something that if you represent using normal grid, it will be very expensive regarding memory. But at the same time, the start and the goal locations are fixed. Okay. So you don't need to build a general map that that covers or have a high coverage that covers most of the areas in the map. But you need to just build a route from the start to destination. But you don't have a map to do that. So you will build a map customized based on the start and the goal locations. Okay. And for that, we use what's called random exploring random trees. Okay. So it's not a general graph like the probabilistic roadmap, but as the name suggests, it's a tree. And a tree has some very, special characteristics. It's a special case from a general graph. Okay. So we use that RRT to do that. So let's see. Yeah. So as I said, in many cases, the start and the goal locations are fixed. Okay, so you need, so BRM will not be optimal for such situation because in PRM we need higher coverage all the time, because this map will be that we will build using PRM will be used again and again with different goal and start locations. So you need better coverage for it or higher coverage for it. But here, the goal and the start and the goal locations are fixed. Okay, but still there is no map. So we need to build a map, but around the start and the goal locations. So that way we may need less number of nodes. Of course, less memory, which is good. Okay. But of course, since the map that you will build will not, and you will build it fast, very quickly, okay, rather than BRM. But the problem is that maybe the map that you will build will not have high coverage for the environment that the robot is moving in. Okay, so for some reason, even if the start and the goal location are fixed, but for example, some a change happens in the environment, a new obstacle or something, is built in this geometry, then you need to rebuild the map again. Okay, and that would be advantage for BRM in that case, because BRM is usually a general, map. Okay. So what is a tree graph? A tree graph, something like what's shown here. This is an example. Okay. Uh, each node has at most one parent. So if you look here, each node has one parent. This node here, the starting node, has no parent. That's why I say at most one parent, because you may have many of these in a general tree graph. Okay, many nodes that has no parent. But at the same time, any node has at least one child. So look, for example, this node here has 3 child. Okay. So a tree is usually, of course, except the last nodes. like for example these nodes here. Okay, but any node in between the end nodes, okay, and the start node, which we call root, okay, the root node has at least one child. To go from a node to another in another branch, so you see here there are branches, like there is a branches here, okay. For example, if we want to move from this node to this node, okay, these are two nodes in separate branches, so we need to go to reach the common parent, and in that case between two, this node here 2 and this node here 5, the common parent is 4. So we need to go to 4, and from we go to 5, or the opposite, from 5 to go we go to 4, and from 4 to go to 2 we go to 2. Okay, and the most important characteristic is that there is no loops. Okay, and what is loop? Basically, if for example 2 here is connected to 4, then you will have a loop like this. So let's draw it. So if there is an edge between 2 and 4, oops, there is no control Z. Anyways, if there is no, if there is an edge between 2 and 4, then this is not a tree, because you have a cycle here. Okay, a loop, closed loop. Okay, so what differentiate a tree from a graph? This is the basic characteristic. There is no loop, and based on that, you can easily, if you have a goal and a start node in this tree, you can easily go from the goal to the start, as we will see maybe in 10 minutes or something. Okay. So this is RRT, not the RRT algorithm. Okay. Again, we have two phases, the building phase and the usage phase, we can say. But this is very interesting, this one, the second one. In the building phase, it's something very similar to probabilistic roadmap. Okay, so we generate a new valid node, and I mean by a valid node, a node that is, not part of an obstacle, for example. So you generate some random x and coordinate x and random coordinate y, and this new node shouldn't be part of any obstacle in a free space, or shouldn't be a previous node, for example, something new. Then we search for the closest node in the tree right now, and set this closest node as a parent for this new node. Okay, but of course, the way between this new node and this closest node, we can say, or closest neighbor, should have no obstacles. Okay, if there is an obstacle between the new generated node and the closest node or closest neighbor, we just avoid, or skip this node and go back to the beginning of the while loop and generate a new node. Okay, one may say, okay, if there is an obstacle between this new node and the closest neighbor, why wouldn't you go to the next one? I mean, if it has many close neighbors, you can go yes, we can do that. Okay, but we will waste some time. So since we will lose some time anyway, so you can go and just generate a new node and have another chance. That's it. So if the closest node has some obstacle, I mean the way to the closest node has some obstacle, we can just discard this new node and generate a new one. And we can also, continue and check another close neighbor. Maybe it may not be the closest, but it's within the ranges and there is no obstacle, so we can take this guy as our parent. That okay, you can do both. Okay, as I said here, if there is if no node can connect within the range, okay, the closest range that we saw last time, then we can skip this new node. Uh, Otherwise, if we could connect this node to another node as a parent in within the range, okay, then we add this node to the tree or the graph, okay. Now another step that is different from PRM, since we have now the goal node known, so we say that if this new node is close enough or the goal node is within the range of this new node, then we connect the goal to this node and we set this new node as a parent to the goal, and we just finish the graph. Sorry, the while loop or the building phase. If we compare this algorithm here to the building phase of PRM, probabilistic roadmap, you will notice that first here it's a while true. It's can, in principle, it can run forever. Okay, until we find a node that is close enough to the goal node. In PRM, we set some maximum number of nodes and we run because we are building a map, whatever the goal and the start node locations. Okay, but here we loop until we find the goal. This may happen after maybe two iterations. That's very fine. Okay, it may happen with 100 node or 1000 node based on the goal location, based on the map itself, and many other parameters. The second phase is actually very interesting, and that's why we will appreciate the use of tree graph, is to build a route from the goal to the start node. Okay, if you notice that the goal node is a node, something like this node, has no child, because once we generate a new node and this node could be connected to the graph, and before we go to the next another iteration, we find that the goal is close to this new node that we just generated. We just finish and we set this new node as a parent to the goal node, and we finish the loop. So the goal will have no child. So this, in our example, in our RRT, this node here, this root node, will be the start node, and one of those, will be our goal node. So for example, if this is, for example, the goal node, okay, that means this node here, number 3, was the last node that we generated, okay, and we connected to 5, for example. Then before going to another iteration, we find that the goal node is close to this node within some range distance. Okay, then we set this node as a parent to our goal, and that's it, we break. Then we go to the route node, route phase, or building or constructing a route between the goal and the start. What we all need to do is that we trace the parent of the goal. So the parent of that node is this node. The parent of this node is this node. The parent of this node is this node, and the parent of this node is the start node, and that's it. We have a path between the start and the goal. Okay, no need to A star, no need to Dijkstra's. These algorithms are used with general graphs, not trees. If you have a tree and the root is the root node, okay, the start node is a start node, and one of the the node that has no child, we can call them leaves. One of the leaves, if this is the root, then these are the leaves. One of these leaves are the goal. Then you just track the parent, I will reach the goal, and that's it. But of course, this might not end up with the best or the lowest cost or the shortest path, we can say, route. Okay, but something simple, very simple to construct. That's the main idea, and it's cheap. Yes.
So we just set up we just basically set up a binary search tree and then assign specific cell to each node. Then is that what the general gist of this is?
Binary search tree and what?
So this is basically just creating a binary search tree, and then each node is just a representation of a cell or or a
Yes, yeah,
location?
yes, yes, that's right. Yes, that's right. Yeah,
Okay, thank you.
yeah. Okay. Uh, yeah. So yeah, this is RRT algorithm. I hope it's clear. We can give you, some, some example on the tablet. Let me do that to make it more clear for you. So let's go to the tablet very quick to do very quick example. You guys can see my tablet.
Yes, we can.
Okay. So basically, we will start from the start node. So this is the start node. This will be our first node in the graph. And let's assume that, this is our goal from the here. Goal. Okay. Then we generate some, some node randomly. So for example here. Okay. And the maximum or the minimum distance to connect any node is maximum distance is, for example, 100 meters, something like that, whatever. And let's assume this distance is 95. So it's good. It's within the range. Then we set the start node as the parent of this node. So this, let's call it 1. So we have the start node. It has no parent. Then we have node 1. It has a parent, which is a start. Okay. Then we generate another node. So for example here. Okay. So the closest is 200. Okay. This is larger than the maximum distance to connect. So we just exclude this node. And generate a new one. So we just break the loop, not break the loop, continue the loop. I mean, going back to the beginning of the while loop. So, okay, here. Okay, now this is the closest. That's good. And this is, for example, 50. So that's good. So this is 2. And again, the start. Then we generate a new one. Let's have an obstacle, for example, like this. Just one obstacle. Okay, we generate a new one, for example, here. So this distance here is, 80. But we have an obstacle in between, so we can't connect it. Okay, so we just, exclude that one. And generate a new one. So for example, it came to be here. Okay, and this is, for example, let's say 100. So it's good. So 2, I'm sorry, 3. And the parent is 1. Okay. Then we generate a new one. Let's say it's here. And this is, 95 or 96, something like that, anything. So yeah, so this is 4. And the parent is 3. Then we generate another node. So for example, it came to be here. And this is 80, for example. So it's good. So this is 5. And its parent is 4. Okay, now we check this distance. It was, for example, 99. So it's less than 100. So we can add the goal and we set its parent to 5. And we break the loop. Now, what would be the path? Not the shortest path, just the path. Okay, we just trace the parents. So we start from the goal. Goal will go to 5. And the 5 is going to 4. So we go in that way. That way. Then 4 is 3. And 3 is 1. And 1 has start. Very simple, very simple. Okay. There is a design choice or a programmer choice. Okay, when you generate something that I will explain, it's just based on the programmer choice. When you generate a node, and that node, has many nodes within the range, within the minimum distance of 100, for example, here. Okay, but the closest one, there is a wall between it and the closest one. For example, let's assume we generate in between a node here. Okay, this is before, of course, completing this code. I mean, I'm assuming so. So this distance, let's assume it's 90. Let's assume so. It's very big, but anyways. But this distance is 50. So these two nodes are within the range. So we can connect to both, to any one of them. But we can't connect to both because we will have two parents. We should have only one parent. Okay. So we started with one, and one, we found that although that the distance is 50, but we found a wall here between this new node and node one. Okay, here is the design choice. He can discard this node and generate a new one. Okay, like what you will see in the code, or he can go, to the next in distance. So the one that has not the minimum distance, but something, number two in if we sort them, which is this node, and he can connect. Okay, if you go with this and have a big list and try to choose if number one, for example, is not there is an obstacle, I can't connect to it, and then you can go to number two and connect to it. Okay, or you just discard it and generate a new node. It's a designer choice. Both are not optimal solutions. Okay, so you got this, guys. It's very easy. It's very simple coding. Okay, so let's see. Let's now go back to the.
Mr. Mustafa,
Yes, Johnny.
I just had a
Yes.
quick question. You
Yeah.
know, when you were writing the nodes for 1 and 2, how'd you know to connect the node 2 back to the start node? Why wasn't it back to the 1? Is it because it had
The
a
distance.
shorter
Yeah,
distance
the
to
distance.
the start
Yeah,
node?
for example, let's assume that was the case. Let's assume that this distance is 50, but this distance is one for 99. Okay, so what is the closest?
It'd be to the start node because
Yes.
50. Oh, okay.
Yeah. Okay. So you connect, your parent will be the closest neighbor to you, but it should be within the range. Should be within 100. If you didn't find any neighbor within 100, then you just discard this node.
Right. And
Okay.
pick a new node.
Yes.
Okay.
Just go back to the beginning of the loop. I'm sorry. Generate a new random node and do the same stuff again.
Okay.
Okay. So let's go back to the. You guys can see the.
Yeah, we can see the slides.
Okay. Okay. These are the parameters that we're gonna play with. Goal node location. This is a very good. This is a really an influential parameter, we can say. Okay. The maximum connect length, the range that I'm saying. Okay, and the number of segments. And I assume you remember this from last time. So to check if there is an obstacle or not, so I can connect two nodes together. We divide the edge between these two nodes, and we check the point along this edge. If any point of them is on button of obstacle, then we can't connect these two nodes. Okay. The last one is not a parameter. I'm very sorry, it may be confusing in here. I will change that. But the last parameter is showing you this is a 2D, a 2D grid. Okay. The number of cells is just the multiplication of the number of rows and the number of columns. And it's actually more than 1.5 million. Okay, it's 1,690,000 cell. Okay, so if we use that huge number of cells with dikestras or a star or whatever, it will take huge time to build a route from the start to the goal. This is the goal. This is the start goal. I'm sorry. This is the start node, and this is the goal node. Okay, it will take. Of course, it will give you a very good, or the shortest path. For example, using a star, but it will take a huge time from you. That's why you need to build a map. And of course, the same applies to BRM. I'm just using the same map like BRM. Okay. Now, if we run the algorithm using these parameters, this is the goal node at 200 and 200. The maximum length between any two nodes is just 200, and the number of segments is 100 to check for collision. Okay. The number of nodes in that map is 127. Just imagine this. You have some representation of the map that the robot will move through. Okay, and this representation is just 127 nodes. The array is 127 rows. Just imagine, okay, if you are playing with this 1,600,000 mesh, how much will be the route, the route array, or it will take very much time, and also very huge memory. That's why we go to such kind of algorithms. Let's play now with the goal location. Let's put the goal in a very bad location like this one. Okay, it's like it's trapped. So because now the goal is hard to be connected, okay, we take much more nodes. So now the number of nodes increased to 330. It was 127. It's more than the double. Yeah, more than the double. Okay, you have here maybe 200 more, 197 more nodes than the previous situation. Just because the goal is, is like a trapped in a very hard to reach place or location. But still, 330 nodes is far, far, far better than dealing with 1,600,000 great cells or nodes. Okay. Now let's make the maximum connected length is equal to 50. That means if you generate a new node, okay, you can't connect it to any node with a distance larger than 50. It was 200 in the beginning, here or here, 200. Okay, now since it's only 50, then you will need to generate a huge number of nodes until you reach to something closer to the goal and connect to the goal. Okay. By the way, the green path is just flowing through the parents until you reach the start node. Okay, this green path in any map here is just the path between the goal and the start node here. Okay. Is that clear, guys? And now we have, in that case, more than 5,000 nodes. But again, 5,000 nodes is far better than dealing with more than 1 million nodes. Okay. I want you to imagine now, if the goal location is not here and here, look, after 5,000, we still far from the goal location. If the goal location is here, like this example. Okay. So you can imagine how much more nodes we're gonna need to reach the goal if the goal is here. Okay, if you combine it both parameters together, less connect length and far, you know, uh, and the difficult location we can say for the goal node. And now let's play with the segments, the number of segments. If you reduce the number of segments, then the probability of having of the error we can say in validating an edge between two nodes become more or greater. And that's the situation here. If you have just one segment, okay, you will just have something wrong like this, and maybe your mistake will affect even the pass. Now if we trust this pass, the robot will collide here at that wall. Of course it will not continue, it will collide here. Of course this is the goal. Or I'm sorry, if we start from the start, we will collide at this point here, and we will not be able to reach the goal. Okay, that's if you choose a low number of segments. This is the final notice that I mentioned to you on the tablet here, is that if you generate a new node and there is an obstacle between this node and the closest node within the range again, then you just discard this node or reject it and go back to the beginning of the while loop and generate a new node. Okay, until you find something that can be connected to some node in the tree. Okay. Okay, guys, any question on that? I just finished, but of course I will now go to the code. Any questions? Okay, so let's.
I was just curious, why was there so many like um for RRT example 3, why was there so many dots like at the starting point, but when it got closer to the goal, there was less?
This one,
Yeah,
like
I'm
here.
just curious.
Yeah, that's fine, because no, that's right. That's a very valid question, because basically this will be the end of the algorithm. Okay, so basically when we discovered, you see this node,
Yes.
here. Okay, so when we discovered this node, this was closer, uh, within 50 meters. The goal was within 50 meters of that new node. That's why we connect and we stop, we break the loop. That's why we didn't generate more nodes here in that area.
Oh, okay, I see.
Here you have a higher number of nodes because you have higher number of connections, because once you generate node closer to the start node, okay, usually the root node has many connections than the leaf nodes, like this one, like the goal node here. Okay, because the philosophy of the algorithm, you generate a node, okay, if it's close enough to some node in the root, in the tree, you connect it to it. Okay, and basically our tree starts from here. Okay, so in the beginning, whenever you generate a node, it should be it should connect. For example, the second node you generate should be connected to the start node. Okay, the third should be connected to the second and the start node. The fourth to third, second, and the start. So, and this second and is within the range of the start node. Okay, so the more you generate in the beginning, the more connectivity will be closer to the start node, closer to the root. Okay, and as we go further, the probability of ending the algorithm will be higher. That's why here, when we reach this node, we stop and we didn't generate more nodes. Okay,
Okay.
so let's now go to the Matlab. Yeah. Okay. Yeah. So the beginning is just the same as, so we have, whenever you change the seed, as I said in probabilistic roadmap, you generate a new map, we can say, okay, or a new exploration. So this is basically the same. So we have the original map is 1300 by 1300 cells, very huge. Okay, these are the obstacles, and here I am showing the obstacle. Let's have a run. Not here. So basically, let me clarify this because you make so so if we plot it from the beginning, yeah. So this is basically the flip of the map. This is not the map. This is just a flip of it, because X here. So if we continue, let me. So now with this command here, I'm adding X and Y, X axis and Y axis. So it doesn't. Ah, I'm sorry. Yeah, I'm sorry. Good. Yeah. So this map was originally built in that way. X is increasing from this point to this point. Okay. But Y is increasing from this point to that point. So here, for example, X is 1. Here is X is 1300. The opposite is for Y. Y here is 1 and Y here is 1300. But we usually, when you draw axes, the axis will be something like this. So X is increasing from that point forward and Y is increasing from that point forward. Okay, so X should be increasing from here to here and Y should be increasing from here to here, opposite to this. So this command here, axis XY, will do that for you. So if we, look, so now X is increasing from that point to that point and Y is increasing from that point to that point. That's why it's flipped around, like mirrored. Okay. IM show by itself will generate for you some image like this, with X increasing from that point to that point, and Y is increasing downward from here to here. So we flip that using this command, axis XY. Then we draw the axis, you see. So Y is increasing from here to here. And we add the axis labels, X axis, Y axis, and we just adding a title and a grid, like, just to be easy to see the coordinates. Here is the maximum connect length. Okay, the range that I'm telling you, that I showed you. So if we generate some node and the closest node in the tree is within 200 meters, that's okay. We can connect it. Other than this, it will be discarded and we generate a new node. The number of segments, of course, should be 100 or something big. Okay. So let's make it 100. And here is some Boolean functions that, variable, which we set true if we find the goal. If we generate some node and this node, we find that the goal is close to this node within 200 meters, then we set this variable to true and we will break the loop based on that value, as we will see later. So let's see now. Node is just, a variable, a counter to count or to track the number of generated nodes in the map. Here is the map. It's exactly the same size as obstacle array, okay? And it will have ones whenever there is an obstacle. And it would have zero if it's a free cell. If it's two, as we will see later, that means there is a point here that in the map. Okay, a node that we discovered or generated. Here is the location of the start node. Of course, this should be an input, a given, based on the problems that you have. And here is, I'm sorry, yeah, tree connection. I forgot this. Tree connection is actually the array that will represent our tree. And we will have the exact similar array in the BRM, but I called it graph connections because BRM generates a graph, not a tree. But here we are generating a tree. Okay. So this array here will contain all the node and its parent. Node, parent, node, parent, just like the array that I built on the tablet. If I can show you very quick on the tablet, that array. So this was the array that was, yeah, this is the graph connections array. Just a node, parent, node, parent. Okay, very simple. Let's go back to the Matlab. So the first node to add to that array is actually the start node, the root of the tree. Okay, and we add the node by its ID, and this is how to change the coordinates or the column and row into ID. So it's just a number, and it has no parent, and I mark this as infinite. So the root has no parent all the time. And we have, so you mark also this location as a node in our map. So we mark it with 2. So map, this map has, if there is a cell with 1, that means it's all obstacle. If there is a cell with 0, that means it's just a free cell and there is no node there. Okay, if it's a 2, there is node there. Okay, so this cell with 2 is part of our final graph, we can say, final tree. Then I will draw or plot the start node. So let's continue and see. Oh, I'm sorry. Okay, so this is a start node here. Okay. Then I locate the goal node. Okay, for example, at 200 and 200. So this is 200. This is also 200. So it should be here, as you will see now. So this is a start, and this is a goal. Okay. Now we go to the while loop. So let's have a stop at some point. Yeah, so let's have a stop here. So in between here, I generate the node and apply all the checks. Let's do that together. Okay, so here I'm generating a random number. Okay, between 1 and the number of columns. And remember, the columns are representing the x-axis. Rows representing the y-axis. Okay. Then I'm checking that this new node is not an obstacle. or not a previous node that I generated before? Okay, if so, I will just continue. I mean, generate a new. I'll discard it and generate a new node. We don't need this. Okay. Then I just create an array here. Okay, I call it distances. I should call it nodes distances or neighbor distances. So let's call it neighbor distances to make it more clear for you what is the meaning of this, or the job of this. So basically this array here will have the closest nodes to the new generated node, but within the range of 200 meters. Okay. Then we will sort it to get the minimum. So let's do that. So we should check the distance between the new node and all the nodes in the tree. So I'm looping here from 1 on to the number of elements. Numel is number of elements. This is a function in Matlab that returns the number of elements in any array. Okay. In that case, here is our array, which actually the first column of the tree connections. Now, of course, it has only one node, so this loop will just iterate one time, because we have only at the start node. So we actually don't need this, but anyways, so this actually was part of the BRM BRM algorithm. So we actually don't need this, but let's keep it for a while. Okay. So I'm saying here in the BRM, the tree connections was just created in the beginning with infinites. Okay. So each time I loop from 1 to the same number. Okay, so I know that I finished the number of nodes that already discovered in the node using these 3 lines. Okay, if I encounter an infinity, I just break and that's it. Okay, but we don't need it actually, but we can just keep it. Okay, but we can remove. Okay, so we get the neighbor, anyone in the any node in the tree. Okay, so for example, if I is equal to 1, here I am getting the ID of the first item in the tree array. Then I calculate the distance using this norm. But if this distance is larger than or greater than maximum connect length, I will just discard this neighbor and go to find another one. Okay. If it is, I go to via obstacle, your homework. Okay, this function that takes these inputs here and return either true or false. True means there is an obstacle between the new node and this neighbor. That's why if this is true, if this return is true, there is an obstacle, so we should discard this neighbor and find a new neighbor. Go back to the for loop and get a new neighbor. Otherwise, this neighbor, I can connect to this neighbor. This neighbor is within the range and there is no obstacle between the new node and this neighbor. So I can, it's a candidate. So I can add it to this array. Okay. We add actually 2 stuff here, 2 information about this neighbor. We add its ID, the node ID, and its distance to the current or to the new node that we generated. Okay. After this node, after this loop here, this neighbor distances array will have all the nodes around the new generated node within the range of 200. And then we can choose one of them, actually the minimum one, the minimum distance, the closest one to connect to. Okay. if the size, so this is a connection, connection part here. But basically before that, if there is a condition to go into that. If the size of this array is larger than 0, that means there is some neighbors, okay, that I can connect to, because and there is no obstacle between, and all of them are within the range. Okay, so if so, I will just first add the current node to the map by marking its location by 2 in the map, and increase the counter of the nodes. So we have now a new valid node. Then I will sort the neighbor distances array based on the second column. And remember, the second column contains the distances. Okay. So after this operation here, or this function, distances sorted will be the same as neighbor distances array, but they are sorted. So the closest neighbor will be the first row, the second closest neighbor will be second row, and so on. Okay. Then I add the new nodes that I generated in the tree connections graph array, and also set its neighbor. So this is the ID of the new node that I generated, and here is the ID of its parent, which actually the first row here. Its closest neighbor would be in the first row of this distances sorted array. Okay, the first row has two elements. The first one is the ID of this closest neighbor, and the second one is the distance between the new generated node and this neighbor. Then I plot this new node, okay, and plot a line between this new node and its closest neighbor or parent. Okay, so let's see. Let's now continue. Go and see. We have here a neighbor here. So the closest neighbor basically is a start node. The closest neighbor is that one. I think either this or I think this one. Yeah. Then this one. It looks boring, but it will finish now. So yeah, because we discovered this one, okay, and the goal is within the range of this one, okay. So we connect and we stop. Then there is another code that I will explain now that makes this shortest path, or not shortest path, just the path. Okay. So yeah. After considering, so let's continue after this point. So let's remove this now. So after adding the new node to the graph, okay, and as I said, if there is no neighbor within the range, then we just continue. I mean, we remove this node. We don't consider it. Okay. I just left this, but I can just remove them for debugging. I put them for debugging to print their values here, but I can remove them. So basically here I am checking if I accepted the new node that I generated, for example, this one, okay, I should check if the goal is within the range of it or not, within 20 meters or not. And that's the part that do that. Okay. So, but it's not enough to be within the range. It should be within the range. The goal should be within the range, and also there is no obstacle between this new node and the goal. So if there is an obstacle, for example, like this here, then we will continue. We will not set this node as the parent of our goal. No. If there is an obstacle between them. So I'm checking two conditions here. The distance to the goal, and it should be, of course, less than the maximum connect length of the range that I'm talking about. And this function should return 0, which means there is no obstacle between. If it returns 1, there is obstacle. If it's returns 0, there is no obstacle. Okay, and the complement of, or the node of 0 is 1. It's true. Okay, so that means the goal is within the range of that new node, and there is no obstacle between the new node and the goal. Then you do all of that. What is that exactly? Add the goal now to the graph and set its parent as this node and just exit. So let's do that. So I'm incrementing the nodes because I will add now the goal node as a new node to the graph. And this is the counter for the number of nodes in the graph or the tree. Okay. Then I will set the location of at nodes to the goal ID. Okay. And I set the parent of the goal as the new node that we discovered, with the ID of the new nodes that we generated or discovered. Okay. And set the location of the goal as, visited or something as part of the graph. And then we plot a line between the goal and the closest neighbor, its parent. And we set this as true. This goal found. You remember, guys, I told you there is a variable that, says that we find the goal or not. Okay. So if we find the goal, we, drive this path, construct this route from the goal to the start node. Okay. And we do that using construct route. It's a function. Okay. That takes the map, the number of nodes, and the tree connections, which has the parent of any node. Okay. And we trace the parent. That's it. Okay. And we return the route in that array. Then for each node on the edge on the route, we mark it with green. That's it. So if we do that example, so let's run from the beginning. Let's do that again together. We first build the tree. Oops, it doesn't stop here for some reason. Oh, it should stop. Let's do that. But now we'll just skip all of that. Okay. So step by step. So we just trace. So the route here has, after this line, the function will return, all the nodes in the route or on the route, and we just draw them or plot them one by one, edge by edge. Each node will be encircled with a circle like this, for example. Look, there is a circle here, and then we plot a line between the child and the parent. Okay. So, any question, guys? So your homework will be to two homeworks. Again, via obstacle. This is the same as just copy and paste. Whenever you get the first one, you will get this. And the shortest path here. This function here. Okay? This will be your homework. Any question, guys?
No.
So Mr. Gustavo has no questions. Okay. Who is the guy that has a problem with his kid, Jose or Saul?
Yes, me.
So okay, so Henry will mail you another kit, a third one.
Okay, I appreciate it.
Okay. So guys, Gustavo and Saul and Johnny, please, the old kits, okay, that has a problem with the capacitor, please bag them again, okay, and we're gonna see some, some solution to get back the kits from you. But I'm just waiting for the answer of Professor Melissa on that, okay? You may, I don't know, you may mail them back. I really don't know what is gonna happen, or drop them somewhere. I don't know, but please bag them again in their original box that you receive, and just keep it aside until we see some solution for it to get it back from you. Okay, and from Saul we will take 2 kits, not just one. Okay, guys, you have any question on that? Okay, looks like there is no questions. Okay, thank you very much. Yes, yes, Gustav.
I told you, I don't know if you see my picture, but my capacitor is bent a little bit, but it looks like it's connected on both sides, so I think it should be fine.
It should be.
But I'll let you know if I have any problems, but I think it's fine.
Yeah, I really don't. I'm not sure also what is the function of this capacitor, because if I know, because the board, the chassis board that you have, okay, has many parts. Each location has its own function. So I even don't know what is the function of this specific location. So I can test it using some, run some code and see if it's running well or not. But I really don't know even what is the function of that part in the chassis board.
Right.
That's why I can't even give you a help on that, how to check that if it's working or not. But hopefully
It
will
looks
be okay.
fine. Hopefully it'll be fine, like you said.
Yeah, yes.
All right, Professor. Thank you.
Thank you very much. Okay, guys, thank you very much. Have a great day. See you
Thank
on
you.
Wednesday, Thursday.
Thank you.
Bye-bye. Thank you.